let's get started here. So last time we started in looking at the dot product. You've had a pre-work on it. You've had a little bit of practice with it. And so let's just remind ourselves of the computation, just to kind of just ground ourselves for the day. The computations a lot of times in this class are just kind of, you got to memorize them, you got to learn them, we move on. But let's just remind ourselves of the computation here. It's a good chance to practice with our vectors. Now, let's say a student comes to me and says, I think the answer is 0, 1, 1. What's going on? Let's forget about the computation, is the answer right, is the answer wrong. Like big picture, what's going on here? Yes, Christian?
The value of a dot product is supposed to be a scalar.
The value of a dot product is supposed to be what type of object? A scalar or another number, right? Okay. So just keep that in mind as you're working through that. That's going to help you organize this math as you learn it. Ask yourself, what type of object am I expecting when I do a dot product? Okay. That's going to help ground you a little bit. And so if we set this up, we'd have 0 times 1 plus negative 3 times 0 plus 1 times 2. And if we simplify that, we end up with the dot product being 2. Now, the dot product roughly gives you a sense of to what degree are two vectors pointing in the same direction. However, it also builds into account the lengths of those vectors. And so you can't say 2 means they're really pointing in the same direction or 2 means they're really not. You also have to take into account the lengths of those vectors as you're thinking about it. And that could be a little bit confusing. Okay. Yes, Dan?
So if it's a positive number, can we assume that the angle between the two is less than 90?
Yes, that you can do. Great observation there. If this dot product comes out to be positive, you know that the vectors are pointing at less than, that their angle is less than 90 degrees between each other. And if it's negative, you know it's more than 90 degrees. And if it's 0, you know that these two vectors are what?
Parallel.
Not parallel, but orthogonal, or another way to say orthogonal is perpendicular, right? They're at 90 degrees to one another. Okay? All right. Here we have a method for finding the angle between two vectors. We looked at that last time. And I'm going to give you this definition here in just a second. But it is so important to me that you start developing this intuition for what a dot product measures. The computation on its own is not, it's not difficult and it's not particularly helpful. Okay? So it is important that you start to get this sense of, okay, if I had two vectors, especially it's really helpful if they're both of unit length, they both have length 1, then you can really see that it roughly measures, the dot product roughly measures the degree into which these two vectors are pointing in the same direction. Here's the result of doing the dot product. And if I keep these vectors at the same length, where is the dot product the largest? When the two vectors are pointing in the same direction. If I keep them at the same length, right? But if I just give you, if I just tell you the value of the dot product is negative 1.4, is that a big dot product, small dot product? It depends because it also takes into account the lengths of the vectors, see? Because here I'm not changing the angle, I'm just changing the lengths of the vectors. Okay, so be kind of careful with that. Spend some time exploring this. It's a clunky looking demonstration. I haven't found anybody do it better, so we'll stick with it. Okay? How we doing, folks? Okay. So those are hyperlinked in your handout. So how would you get to the hyperlink for that handout?
Go to your website.
Go to the website and find those particular in-class notes, and you can click the demonstration hyperlink. Okay? You do need to be spending some time outside of class just exploring these notes, exploring these ideas. Okay? All right. Where are we? So I want to challenge you a little bit with your notation. Okay? I want to push you a little bit with your notation as we go through this. So I want to give a function that describes the dot product. And I want you to think of the dot product as being a function that maps from Rn cross Rn to R. Okay? Now, I'm pushing your notation here. One of my goals, hey Seth, do we have a seat for you? We got one up here. Got a healthy class today. Very healthy class. Good, good. Okay. Wow, full. Okay. I want to challenge you a little bit on this notation. I'm not expecting you to look at this and say, I 100% understand what you're doing with these functions, but I need you to start, like, you're eventually going to get to a math class where it's assumed you know this, and nobody teaches it to you along the way. So I'm kind of pushing you there a little bit. When we do this arrow notation for the vectors, this is understood to be the domain, and this is understood to be the, you would think, it's called the codomain. Okay? Functions map from the domain to the codomain. Okay? Folks, I'm not going to test you on this knowledge right now. Okay? I'm just starting to push you on, or I'm not going to test, I don't think I test you on this at all. I'm just starting to push you on this notation because you do start to need to think about, hey, I've got a thing called a dot product. What does it actually do? And the way you could think about it is it's going to take one vector and another vector, and it's going to return a what? A scalar. That's what that's showing there. Did everyone see that? How does it actually do that? You would do it by taking vector 1 and vector 2 and doing this operation. The sum from I equals 1 to n of ui vi. Yes?
Are you recording?
I hope so. I am. Thank you. Test, yep, it looks like we're good. Thank you. I appreciate you checking.
And do you also, I was just going to ask, do you have extra notes?
I don't have extra notes from last time. No, I'm sorry. I apologize. I sometimes have and sometimes don't. Yes?
If you have like vectors from higher dimensions, are they always going to, like when you dot product them together, they're always going to produce a scalar?
Correct. And so what I've done here, I've not limited myself, like I haven't told you what dimension we're in. We're in dimension n. That could be R2. What would that look like? You take two-dimensional vectors and you dot them together. Or this could be an R3 or even higher. Okay? And so how do you do it? All this says is you take the like coordinates, multiply them together, and then sum all of those up. Now, again, I'm pushing you with the notation because I know that it's a good thing to start doing at this point in your math career. I'm not looking for mastery of this, but I want you to see that that fits with what we did, say, up here, where what did I do to find the dot product? I took two vectors, and then what did I do? What was the actual coordinate operation that I did? I took this coordinate times this coordinate. That would be u1 and v1. I multiplied them together. Then I took this coordinate and this coordinate. That would be my u2 and my v2, and I multiplied them together. Then I took my u3 and my v3, multiplied them together, and what did I do with that result? I added them all up. That's what this is saying to do. And so that extends to any dimension you want. Christian, we are in trouble today. We have no seats, which we got plenty of chairs though.
You have a chair there.
I think this one works.
There's this
Oh, there's a chair? Wonderful. You just need a chair there. Great. Yeah.
Sorry, I'm late, by the way. Sorry.
That's all right. That's all right. Okay, so folks, I'm challenging you a little bit on this dot product notation. I think I would encourage you to, I mean, if you're going to be doing math in your career, spend some time thinking about it. If you're not needing math for your career, well, I don't know why you're in here, but I guess skip it, okay? I do want you to take some time to work through this demonstration that I just showed you. That was that vector dot product demonstration, and I want you to write down, jot down some stuff here, so you fill in. Okay. We define two non-zero vectors to be orthogonal if their dot product is what?
Zero.
If dot product is 0. Okay. Put another way, what I'm saying is if I take u and dot it with v, if I get 0, then I know that they are orthogonal. Okay. Now, one way to think about that is not to use the coordinate definition of the dot products, but to go back to the geometric definition. What was the geometric definition of the dot product? Do you remember? We gave two definitions, a geometric one and a coordinate one. What was the geometric one?
The magnitude of u times the magnitude of v times the cosine of the angle between them.
So we take the length of the first vector times the length of the second vector, and then multiply them by the cosine of the angle theta between them. So given two vectors that could have various lengths, what dictates whether they're orthogonal? Well, to force, if as long as these vectors, and I said they have to be non-zero, so their lengths aren't 0. So the only way of these three numbers here, length of u, length of v, and the cosine of the angle between them, the only one that can possibly be 0 is cosine of theta, and the only time cosine of theta is 0, well, I shouldn't say the only time, for an angle between 0 and 180 degrees, or 0 and pi radians, the only time the cosine of that angle is 0 is if the angle is pi over 2, or 90 degrees. Okay? So the only time two vectors are orthogonal is if their dot product is 0. Okay? How are we doing? Okay. All right. So again, I'm pushing your notation. Back up above here, I'm not going to repeat the cross product cross product example, but please, one, does order matter with cross products? Yes, it does. So slow the heck down. They're anti-symmetric. Okay? Order matters with cross products. We did a pre-work on how to do cross product multiplication. We learned how to do that, and we've worked this example here. Okay? Do some more practice. Did I in your pre-work link you to a faster way to do, or not, I shouldn't say a faster way, another way to do the cross product? Did I show you that in your pre-work? Somebody shoot me an email, I'll send you a video. There's lots of gimmicks, and in fact, even this is a gimmick. The reason why I teach it this way, though, is it extends to something that you do in linear algebra, and you'll want to be able to do it in higher dimensions in linear algebra. But there are other gimmicks for showing how to do the cross product. This is one gimmick. There are others, and so do some digging on the internet, see if you can find tricks for computing cross product, and you'll find one. If somebody emails me, maybe I'll find that video and send it out to the class. I don't teach it because it doesn't. It's a one-trick technique. It only works for one thing, and I'd rather show you this method. So anyway, we've learned how to compute the cross product. Okay? Being a little bit more abstract, let's talk about what the cross product does. The cross product is going to take one vector and another vector. So it takes two vectors at the input, and what does it return?
A new vector.
Ooh, what's that?
A new vector.
It returns a new vector. Does everyone see how I'm showing you that you take two vectors, you do something with them to return a new vector? Okay. Where the way you would take the cross product of the vectors u and v is just to compute this determinant right here, I, j, k, and then we need to get the coordinates in the right order. If I'm doing u cross v, this would be u1, u2, u3, v1, v2, v3, and you do this computation, which is what you learned how to do in your pre-work. Folks, if you're finding this notation challenging, good. I found it challenging. Okay, I found it challenging, but I didn't learn about it until I was kind of underwater in a class. Okay, so I'm kind of stepping you forward with this challenging cross product notation. Okay, or these challenging function notations. I do want you to start thinking about, where does this object live? When I do an operation between these two objects, I get something new. What do I get? Where does it live? We want to start thinking about things like that. Okay, so I'm starting to lay the foundation for that. Okay, folks, I do recommend. Oh yeah, Dan.
So you say it yields a vector in Rn. What if we have a vector in R2 crossed with a vector in
Whoa,
R3?
what a great question. These are the same. These are the same. Oh,
Would they be different?
folks, I have an error in my notes. Okay. First of all, you could not do that cross product. But even more importantly, there's only the cross product is only defined for what types of vectors? Vectors in R3. And that's what that said there, and I didn't catch myself. So folks, I had an error there, so I really appreciate the question, Dan. It's a great question. This should be R3 to R3, and it returns a new what? Vector, and it returns a three-dimensional vector. Okay? So the cross product, interestingly enough, is only defined in 3 dimensions. That's okay, though, because what? if you're going to go on to take some physics classes, what do you study? Physics in 3 dimensions. So it works out pretty well for us. Okay. Does that make sense, folks? So, but just so you know that if I put an in there and in there and in there, it means you have to take them from the same space to be able to do something with them, to answer your question,
Okay.
even though I had the error. Yeah, great question. Okay, folks.
Well, wait,
Oh.
sorry, that begs the question then, so can you not, dot 2 vectors, like?
Yeah,
from
so
R2
these,
and
so up
R3?
here, when I wrote this, when I did my dot product, these do have to be in the same dimension. Let's try to do it. I mean, let's take this vector which lives where? How do you know, where's this vector live?
R2.
How do you know that?
There's 2 numbers.
There's 2 coordinates, it's 2-dimensional. Let's try to dot it, with this vector right here, try to dot it. What would you do? You would take this coordinate times that coordinate, this coordinate times this coordinate, and
0.
you're stuck. No, you can't call it 0, you can't invent something.
So there's no implied 0k in the first vector?
No, not if I've written it this way.
Okay.
Yes. Now, that actually gives you some hints for how you might do some problems. And sometimes in math, what you do is you might add an extra dimension to the problem. But as I've written this vector, it lives in R2.
Okay.
It's not the same as the vector where I put a 0 there. That vector lives in R3. It's a 3-dimensional vector. You can draw connections and mappings and correspondences between them, but they're not the same.
Okay.
Yeah.
Thank you.
So folks, we will be using this Wolfram, what's it called? Wolfram CDFs in here. They're built into a lot of your MyLab math exercises. They're constantly updating. I don't know whether you have to install Wolfram CDF in order to do your exercises. Now, they might have made it so that it's all cloud-based now, so you don't have to do that. I'm not sure. Okay. But if you do need Wolfram CDF, there's the MyLab Math shows you how to do it. But I went ahead and just downloaded the Wolfram CDF player, and you might find that helpful. It's something that I'll talk more about if I need you to do something with this. Okay? But I want to show you this demonstration here, which gives us a, let me minimize it, which gives us a really interesting way about thinking about the cross product. And what I would like to restate from what I said before, it's a little bigger. Kind of the wrong size. That'll help. I'd close the doors, but it'd get way too hot, way too fast in here. Is that the way I taught you how to compute the cross product in your pre-work was just a gimmick. Okay? That was a gimmick. It gives us the correct answer, and so that's what we do. Okay? We don't actually know what the cross product is just yet, and we're getting ready to define that. Okay? Now, we do know, based on what I wrote there, that the cross product should take 2 vectors, careful, in R3, and return a new vector in R3. So we already know that the object is supposed to be a vector. So if I want to describe the result of doing a cross product, which is a vector, I need to have a what and a what?
A point and,
Careful, that's for maybe think about lines or planes or something.
oh,
What, if it's going to be a vector has to have what? Magnitude and direction, right? So how do we find the direction that the cross product points in? That's with our right-hand rule. Remember that? That's what we kind of talked about. I think it was at the very end of the video. So if I give you 2 vectors in R3, this one pointing in this direction, this one pointing in this direction, line them up with your index and middle finger in the order in which you're multiplying them. Right? And then your thumb will point in the direction of the new vector. Okay? That's called the right-hand rule. So how do we find the direction for a cross product? With the right-hand rule. That's the direction that it points in. Okay? So what else do we still need to find for a cross product vector? We need to figure out what its magnitude is. Okay? So we figure out the direction by the right-hand rule. The true kind of geometric definition of what we mean by the cross product is a vector whose direction is determined by the right-hand rule and whose magnitude is determined by the area of the parallelogram spanned by the 2 vectors. That's a huge mouthful that's going to take a little while to absorb. That's why I've got this demonstration for you to play around with. Okay? So here I've got, because it would be really hard to make a three-dimensional manipulative, here I've got R3, 3 dimensions, but I'm going to just, for the sake of being able to build something, I didn't build this, whoever built this, for the sake of being able to build it, they kept the two vectors that they want to cross multiply in the XY plane just to make it a little easier to work with. Okay? So what you are able to do with this, though, is you're able to move these vectors around. Okay? So, if I want to compute, let's worry about the direction first. Let's go ahead and compute vector v crossed with, folks, I think I said these were in the XY plane. It looks like they're in the YZ plane. I'm sorry, they're stuck in the YZ plane. Does everyone see that? Okay. If I want to compute the direction of V cross W, we should all do this together, with your index finger of which hand?
The right.
It matters, with the right hand. With your index finger, point in the direction of V. With your middle finger now, point in the direction of W. Your thumb now points in the direction of their cross product. Does everyone see that? So you see when I have V here and W here, the cross product's going to be pointing along my positive x-axis. Notice what happens if I do some swapping around. Now, with your right hand, what computation am I doing? I'm not doing W cross V, I'm doing V cross W, right? So with my index finger, how are there not enough seats in here? It's crazy. It was my index finger point in the direction of V. Here's V. With my middle finger, I'm going to point in the direction of W. And now my thumb is pointing in the direction of their cross product, which is pointing along which way? Not the positive x-axis anymore, but the negative x-axis. So here you can see, right here where they swap over, that's where the cross product changes its direction. Okay? Now, in reality, these V and W could be anywhere in 3 space. I can orient them however I wish. Okay? So, I don't know, you're in groups. One person in your group, point in 2 different directions. One person in your group, point in 2 different directions. Everyone else, figure out with their right hand, so the right hand's the first vector, figure out the direction of their cross product. Point, does that make sense? So here, Isabel's pointing this way. Let's all work together here. Isabel's pointing this way, all right? With your index finger, point in the direction of the right hand vector. With your middle finger, point in the direction of the other one. What's your thumb going to do? It's going to point upwards. That's the direction of the cross product. Does everyone see that?
Yeah.
Does everyone see how we do that? It could be in any 2 directions. You don't have to point, you can point in any 2 directions, and then somebody else can come along and figure out the direction of that cross product vector. Okay? So again, what's a cross product? It's a new 3-dimensional vector whose direction is determined by the right-hand rule. What else do we need to know, though? We need to know the magnitude of that vector. The magnitude is the length, right? The magnitude of the cross product vector is equal to the area of the parallelogram spanned by those 2 vectors. Okay? So watch what happens as I bring this vector kind of out a little bit. What's happening to the area of this parallelogram?
Growing.
It's growing. What's happening to the magnitude of the cross product?
Also growing.
It's also growing. Now what's happening is I continue to make vector V, as I continue to drag it out. What's happening to the area of that parallelogram?
Shrinking.
Shrinking. What's happening to the magnitude of their cross product?
Shrinking.
It's shrinking. Okay? If you were to compute this area right here, this area would be 2.774 square units, which corresponds to the length of its cross product vector. Okay? That brings up a really important point. What if these 2 vectors, let's see if I'll play, may not, I have to go to the list plane. All right. What happens is I bring these 2, maybe say 180 degrees to one another. What's the area of that parallelogram?
0.
The area is approaching 0, so what's the magnitude of that cross product vector doing?
Shrinking.
Shrinking. So in fact, if the cross product comes out to be 0, then we know that the two vectors are parallel to one another.
Is that the same as the 0 vector?
Yes, when I say 0 there, I meant, so let's be careful. The 0 vector has magnitude 0, right? So as the area becomes the number 0, as the area, so this area for this blue parallelogram becomes the number 0, the magnitude of the cross product starts to approach what?
0.
0, and the cross product vector that you would get from doing the cross product operation approaches the 0 vector.
Okay.
Yeah, great question. So folks, again, I think a nice handy demonstration to play around with. My guess is that what I'm saying right now is starting to make a little bit of sense, and my other guess is in 3 weeks you're going to forget this. Okay? I don't have anything more to say about it, right? But that doesn't mean you've got it down 100%. You need to play with this diagram a few more times before you really get it. Okay? So again, although I taught you in the pre-work a geometric way of computing the a coordinate way of computing the cross product, that was just a gimmick. The trick worked out that way, so that's what we do. Okay? And it's actually related to the exact computations you would do if you were trying to find the area of a parallelogram and then multiply by the direction. It's kind of cool to see it worked out. But the true definition of what we mean by a cross product is it's a new vector whose direction is determined by the right-hand rule and whose magnitude is just the area spanned by those two vectors. Okay? That once you've got magnitude and direction, you've got your vector. So again, so what we just saw when we looked at that demonstration is that u cross v, the new vector, was what? Well, if you follow that right-hand rule, that new vector is orthogonal to both the other two vectors. Everyone see that in that demonstration? Should I go back to that? That this cross product vector right here, it's orthogonal to both of these vectors that were constructed, right? So if I have two vectors and I want one to be orthogonal to both of them, the best way to do that is to take their cross product. So we saw that this was orthogonal to both vectors, while its direction was determined by the right-hand rule. Okay? What we saw in that demonstration was that the magnitude of the vector u cross v was equal to the area of the parallelogram formed by those two vectors. Okay? Do you see why Calc 3 is so hard, folks? The computation's easy, right? The computation's easy. Conceptually knowing what we just did involves spending some time with this image and spending some time with your right-hand rule. And I can show it to you once or I can show it to you twice, but you have to spend some time kind of internalizing that. That is the take-home point of what is the cross product. It's a new vector whose direction follows the right-hand rule and whose magnitude is the area of the parallelogram spanned between them. Okay, let's move on. In this section, we're going to look at the topic called projections. Okay? We're going to be looking at the projection of vectors onto other vectors. So, folks, when I was a math student, I was very literal, so I never took the time to think about names. Think about the word projection. Like, remember, you guys probably didn't have film strips. You guys probably didn't have film strips, or like your favorite day in 2nd grade was when the teacher wheeled in the projector and they put in a little 8mm movie and you'd watch it or something like that. Okay, I want you to think about the word projection. Okay, where you like the projectors like we have up here, where back in the olden days you put a piece of film and you shined a light through it and it would cast an image on a plane. That actually is a very apt description of what we're talking about here. Casting shadows onto other objects. That's how I want you to think about a projection. Okay? So because projections are so important, elsewhere in mathematics we're going to talk about them a little bit more generally before we get into vectors. So below is Below and to the left is shown a solid object living in where? R3. Okay. By the way, folks, now that you've done your pre-work, you can actually say a little bit more about this. Notice that this quadric surface here is, well, if you looked at its two traces, this is what you learned how to do last night in your pre-work, right? The trace, if I cover up this trace is a parabola. If I cover up the x, that trace is a parabola. Okay? And then if I cover up this y, that would be, if these were different values, or if I covered up z, these different values would be ellipses. So this sketch right here is called an elliptic paraboloid. I'll give you some hints on how to name things. I'm going to go over how do you know these namings of these surfaces in a little bit. But this is called an elliptic paraboloid. That's what we learned how to do. And the way you look at it is you look at their traces. Okay. So again, the traces here, the three traces we could look at are z equals 2x squared, z equals y squared, and then if z were 0, we'd have a constant is equal to 2x squared plus y squared if z were some constant or 0. And those are ellipses. So that's why it's an elliptic paraboloid. Okay? If you're worried about how to name it, I'll talk about that in a minute. I'm going to give you some hints. But this idea of looking at the traces is what you did last night. Okay? Likewise, this is also an elliptic paraboloid, except this one's inverted. And so we've got two elliptic paraboloids meeting one another. Okay? You didn't know that until last night, but now you do. Okay? Folks, you've got a little bit of time to learn how to draw these. Okay? You're never going to have perfect sketches. I couldn't draw that perfect sketch. What I could do, though, is draw an upward-facing paraboloid, and then draw a downward-facing paraboloid, and then start talking about the boundary of their intersection. Yes?
Why wouldn't that be an elliptic cone, since z squared would be over c squared once we divide out the...
So the elliptic cone would be z squared is equal to 2x squared plus y squared, and that has to do with their traces.
Okay.
Yeah. So let's hold that off until we get to our quadric surfaces, hopefully later today.
Okay.
Let's hold that question. It's a great question, but let's hold off for just a little bit. Regardless, though, folks, I've got this surface. I want to talk about the projection of this surface into the xy plane. So here you can see I've sketched all of R3. Everyone see that? Where's the xy plane? It's down here, for the way I've oriented it. I want you to think about the word projection. Remember I said it was like, projection day when the light passed through the film and it cast a shadow on the projection screen. I want you to think about shining a flashlight down the positive z-axis onto the xy plane, or from both directions, and you could imagine the shadow that's cast there. Does everyone see the shadow that's cast by this? So this right here is the projection of our surface onto the xy plane. That shadow, in fact, is labeled as R. Okay. Sometimes people have a hard time thinking about shadows, and technically to do the shadow, you'd have to do it from both directions, because I could actually have some of the surface down below here. So a better way to think about it, so you guys are all college kids, and if you take a soda pop can, right, and you stomp on it, and you smash it into the xy plane. Right? If you were to smash this surface into the xy plane, that's what it would look like. Does that make sense? Okay, how are we doing here? All right. So here, what I want you to do is I want to talk about sketching the projections of this surface formed by these various intersections. I want you to project them into the xy plane, the xz plane, and the yz plane. Okay. So let's go ahead and sketch here's my xy plane. Okay. I'll do this first one with you. Let's project this surface into the xy plane. When I project this surface into the XY plane, it would look like, oops, let's go ahead and draw it. Let's see here, I had it color coded and that was kind of nice. If I were to project this into the XY plane here, that would look something like so. And we could give a name to that surface when I projected it into the XY plane. The picture that goes with that is I want you to think about taking this as if it were an aluminum can and smashing it down along your z-axis into the XY plane. Is everyone able to imagine that? Okay? So what I'd like you to do is in your groups, I want you to also project this into the YZ plane and into the XZ plane. The YZ and XZ planes. They're going to be different images. Those projections will look different in those different planes. What just happened there? What just happened there? Oh, goodness gracious. Folks, I apologize. You just keep working. Don't watch what I'm doing, please. I need to just fiddle battle with this.
One of them for just the Y is going to be on the right side of the taller than the X and Y.
Since you're like shining it like this way, you guys think
It's kind of
like the curve. Yeah, for the most, like there's going to be very. Well, there's three small differences.
Yeah. Well, two of them are just
Oh yeah.
It looks more like an exponential to me.
I think they are.
Yeah, I was looking, they're all on the exact, but still technically they're positive in all the directions. So go down like this distance. Would it be smaller than? Okay, I think that looks sort of, but it's.
Yeah.
Hard to tell, but I think it'd be smaller.
Folks, let's today, for this discussion, not worry too much about getting these shapes right. One of these is more of a paraboloid, parabolic shape versus one of them being more of a semicircle shape. Let's not worry about that for today. However, if you were to take and smash this graph into the YZ plane, you'd get a shape something like that. Okay? And if you were to take this graph and smash it, this three-dimensional surface, and smash it into the XZ plane, that's what it looked like. Now careful here, folks. It's customary when we draw these in our class for this to be the positive x-axis, and this to be the positive y-axis, and this is the positive z-axis. They're the ones that are sketched, and if I wanted to draw the other ones, usually I do them in a dashed line to refer to the negatives. But do you see that you kind of have to take this, for this XZ plane here, you kind of have to take that image and rotate it, because we're going to put our positive x right there. Okay? So if we're just drawing two dimensions, we usually orient it the same way we've always oriented it. So that can cause some kind of confusion as you take this three-dimensional shape, you smash it down. Hopefully we all kind of see, like if I smashed it literally, keeping it in R3 here, that shadow would be right there. But then I took that and rotated it this way. We okay with that? Okay, we still haven't actually defined what a projection is, okay? And that's okay. but I want to talk about the projection of one vector onto another vector. Okay? So this was just to kind of introduce the topic of projections. We specifically now want to project one vector onto another vector. So here, what I'm going to do is I'm going to take and I should be careful. Do I say it here? It doesn't say it. What we're doing here is the orthogonal projections. Let me go ahead and specify that somewhere. The orthogonal projection. Okay. So what I mean by that is I'm going to take and if I were to form a plane by these two vectors that I've sketched here, then I would take a plane that's orthogonal to that. Okay, it's kind of hard to talk about. Let's see here. Could you imagine this is the plane that those two vectors live in? Okay. That's the plane that these two vectors live in. So then I'm taking this new plane that's orthogonal to both of them. Okay. I'm going to take that out because that's a little bit messy to see. And so once I've got that, I'm going to project downwards, orthogonally downwards, this vector u onto vector v. So first of all, we're going to write that as the projection of vector u onto vector v. That notation's a little bit strange, and I don't know that it's consistent from book to book, but I think about doing this. This is read as what? How do we read this, folks? It's the projection, and technically it's the orthogonal projection of vector what?
U.
Vector u onto vector v. Okay. It's the projection of vector u onto vector v. So that notation seems, so the way I would read this is the orthogonal projection of vector u onto vector v. Okay, let's read that all together. The projection of vector u onto vector v. Everyone see how we read that? Okay. So it's going to be a new vector. Okay? But it's just the component of the, it's like, it's coming up with this, constructing this new gray vector right here. It's kind of light in this picture. It's this gray vector right here. Are we having trouble? Is this playing? Let me, real quick, folks.
But in the homework, I was like,
Yeah, that's his, yeah.
I had to look at a lot of examples in the class.
Yeah, I was like,
So my math lab, the videos don't work for me right now. So
Mine was like,
extra. Yeah, yours aren't either.
like for the first one it was, and then I did the second one.
Yeah, me too. Yeah.
So
So yeah,
it was the
I'm just
website.
like trying to figure it out. Yeah. I'm not finished.
yeah.
I gotta do.
All right, how are we doing with that idea of a projection, folks? Okay. So we need to come up with a way of finding that projection vector. Yes, Ben?
I was just wondering, is it correct to think of that projection as a component vector of u, but instead of a component that goes along an axis, it's the component that goes in the same direction
Yes.
as the vector it's being projected?
That's a good way to think about it. And we're gonna specifically look at if you've done normal components and parallel components of forces on planes in physics classes. We're gonna be doing projections to do that. Yeah. Yep. Good. Okay. I think of a projection as blank and a. I think I probably have the word collapse. I don't have it there. As collapsing an n plus one dimensional object onto an n dimensional object. Okay. So one way to think about that is this vector u lived where? In R3. In this picture anyway. In this picture, this vector u is living in R3. And what am I doing? I'm collapsing it into a plane. What's a plane? A two-dimensional object. Okay? So I think of that as, and if you look at these pictures up here, we had these three-dimensional surfaces that I collapsed into two-dimensional regions. Okay? So I like the word collapsing when I'm thinking about projections. Okay, so folks, we're just to practice this, we're gonna get a couple of projections right just by inspecting them. Okay? But this will not be a good enough method, but hopefully it builds our intuition, and then we'll go ahead and build a formula for our projections. Okay? So let's consider these two vectors, and let's find the projection of vector what onto what? Vector u onto v. This one's about kind of as straightforward as it comes, because this is already sitting on the x-axis, so to Dan's question, finding this projection is the same thing as finding the x component of this vector. Okay? But in later instances, it'll be like we're like a different coordinate system almost. Okay? So if I were to think about projecting this down, so there's the orthogonality of that projection. It's going to give me this new vector right here in green. So in this case, what would we say? We would say that the projection of vector u onto vector v would be which vector? Well, what vector did I just draw? This is the vector
3i.
You could do it in those components. I'm going to go ahead and do it as in our book vector components as vector 3, 0. Okay. You could also write it as the vector 3. Just as a reminder, folks, because we've only had 2. I wish we could have a month with vectors. We don't. We just get a couple of quick crash lessons on them. Okay. There's the vector 3, 0. Or we could do, in terms of components, this would be 3i hat plus 0j hat, and you don't have to write the 0j hat if you don't want to. Okay? Everybody see how we just wrote this? Either one, any of these answers correct, I have to take all of them. You have to interpret all of them. Okay? If I write it this way and you write it this way, you need to know that we wrote the same thing. Okay? Yes?
Is it advantageous to write the j hat, like you said when
Nope.
writing in
Okay.
brackets?
Yeah. Let's just do this. 3i hat. This one is fine, except the reason why I don't like this notation is it's no longer clear whether we're talking about a one-dimensional, two-dimensional, three-dimensional, four-dimensional vector. Right? It's no longer clear.
So by writing out the
This tells me that we're in R2. This tells I don't know what we're in.
okay. Is there a standard way to do that? Like if you include the 0j, does that then imply that
Yes,
we are in
that
R2?
implies that we're in R2.
Okay.
Because I didn't also include the 0k hat.
Okay.
Right?
Thanks.
Okay, so let's take a look at this one, folks. This one's a little bit harder. Okay, so instead of saying that we use the phrase we're projecting vector u onto vector v, but really another way to think about it is we're going to project the vector u, in this case, because we're in R2, onto the line spanned by vector v. So if I were to sketch a line for that vector v is building here, does that work? Yeah, that works. We got lucky. There's this line here. I extended it through. Does everyone see that? Okay. So now, if I were to do the orthogonal projection, let's see what did I use last time. I used black. For the orthogonal projection, there's 90 degrees there as best as I can draw. If I do that orthogonal projection, it's going to give me this new vector. Okay. Again, it's only in these two examples. I mean, you'll have some in your homework, but it's not common to be able to just guess what the vector is by drawing a picture. Usually, you have to do computations to figure this out. Okay. So, what is this vector that I just sketched? I just said that the projection of vector u onto vector v is equal to, what's that vector? This would be the vector. Looks like -2, -2, or any of the other myriad of ways of writing that answer. We having fun yet? Starting to. How are we doing? Questions? So now that we are starting to build an intuition, so this happens a lot in this class, where we spend some time building an intuition, and it is important to get that intuition down. A lot of times students skip going back and getting and revisiting the intuition, but now we want to focus on the computation. And what often happens is we build a formula, and the formula looks nothing like our original intuition. Okay? And that can be really hard to kind of put those two ideas together. You've got the intuition, you've got this formula. Sometimes you'll just have to trust the formula that it was built correctly, Other times I'll try to give you some hints as how you would remember it. Let's see what's going on here. I want to develop a formula for computing this projection. Okay? So let's just do it. Let me just draw two vectors. Here's vector u, and maybe here's vector v. Okay? And what we notice is I'm going to be collapsing this vector u, whether it's two-dimensional or three-dimensional. I'm either collapsing it onto a line or onto a plane, or higher dimension, but I'm collapsing this vector u onto vector v. Okay? So what I'm looking for is this vector right here. This blue vector right here would be the projection of vector u onto vector v. Now, if I'm trying to come up with a vector, I need two things. What do I need? A direction and a magnitude. Okay? Let's deal with the magnitude first. This length right here can be found, even though these are vectors, it can be found with standard trigonometry, right? We can make this right triangle, because this was our orthogonal projection. We've got this right triangle. That's not the prettiest right triangle. Can you live with it? We've got this right triangle here. So as long as I knew the angle between these two vectors, let me make this picture a little bit bigger. That's kind of, this OneNote kind of plays with that a little bit. Folks, you don't need to erase anything. I'm just going to make the picture bigger. There was my vector u. There was my vector v. My orthogonal projection vector will be this blue vector right here. And I'm getting that. I'm going to get the length of that vector just by ordinary trigonometry. Okay? So how would I find this length of this blue line here? So the length of the blue line is just the length of the what trig function are we going to use? Cosine, right? So we've got cosine here, and the cosine, remember, I don't know how far back it was the summer. Okay, cosine is the ratio of the adjacent side over the hypotenuse side, right? So in our case here, we would have that the cosine of theta would be the length of the adjacent side. That's what we want to find. Okay, that would be, one way to say that is that would be the magnitude of that projection vector divided by the hypotenuse, which, what's the length of the hypotenuse? It's just the magnitude of vector u. So put another way, the length of the blue line would just be would be the magnitude of u times the cosine of the angle theta between them. So that's the length of that blue line. Everyone okay with that? So what if I, oh yeah, go ahead.
You wrote projection of v onto u, shouldn't it be u onto v?
So we read this as the projection of vector u onto vector v.
Okay.
And that's a little bit confusing in that notation. So I think of it, it's the projection of what? U onto what? Specifically vector v.
Okay.
Yeah.
I had it backwards.
Yep, that's okay. How we doing, folks? So now what have we got? We've got we're trying to find the projection vector. What do we got? The length, the magnitude of it. What else do we need? But what direction is this vector, this blue vector pointing in? What direction is it pointing in? The same direction as vector v. Okay. So what we'll do is we'll just take v's directional unit vector and multiply it to that length. So our projection, so the direction of the blue arrow is just the direction vector v divided by the magnitude of vector v, or if you like, 1 over the magnitude of v times vector v, right? That's the unit vector, that's the direction we're pointing in. How are we doing, folks? Okay. And so at long last, we've got this line pointing in this direction, right? The length of this line, we're going to go out in that far, pointing in that direction. So the projection of vector u onto vector v is just going to be the magnitude of u times the cosine of the angle between them times vector v divided by its magnitude. This is the I don't know how this feels. This is the intuitive formula. Okay. Where we got the magnitude. When I look at this, folks, I see two parts. I see this is my direction, or excuse me, this is my length, or my magnitude, and this here is my direction. So we've constructed a vector, and notice that the answer is a vector. Does everyone see this? There's a lot of stuff happening here. Magnitude of u, what's that? A number. Cosine of the angle, what's that? A number. Divided by the magnitude of v, what's that? A number. So this is just some number, scalar multiplied to vector v. Do I have a vector as an answer?
Yeah.
Yes, I do. Okay? It's always a good check to make sure we got the object we were expecting to get. Okay? So I hate to say it, but I kind of think of this as, and I said direction, let me say direction vector. Just to, again, here's a scalar multiple times a direction vector. So you see that? That's our solution. So I hate to say it, that's kind of the intuitive definition. Okay? What we often do in this class is, especially when we see theta showing up, is we try to write things in terms of other vector operations. Okay? Where else did we see a cosine of theta show up?
The dot product.
In the definition of the dot product. So what we'll do is we're going to take this answer right here, and we're going to do some rearranging. And folks, I've not gone through with my notes, and I wanted to put this way over on the other side here, so we're going to kind of work this way back. I apologize for that. So I'll try to get my positioning pretty close to right. And I'll have magnitude of u cosine theta times vector v over the magnitude of vector v. Careful, folks, what's this dot? That's just scalar multiplication dot. I probably shouldn't put any dot there at all. That's just scalar multiplication. It's not a dot as in a dot product. Okay. Now, we just said, though, that this kind of reminds me of what operation, because I've got a cosine of theta in there. A dot product. So let's see if we can build a dot product in this. Okay. Remember that definition was u dot v is equal to magnitude u, magnitude v, times the cosine of the angle between them. So look at, I've already got a magnitude u and a cosine of theta being multiplied together. I'm almost ready to replace this symbol right here with a dot product. But what am I missing? A magnitude of v. Okay. So in math, you give yourself what you want. So I'm going to multiply this by magnitude of v. But what? Then you pay for it by making sure it's legal. Okay? Right? I gave myself what I wanted, which was a magnitude of v upstairs. But then I divided by the magnitude of v to make sure that I was just multiplying by what number? 1. Okay? So look at, if I just do some rearranging, what I would have here is the magnitude, let's see here, let me go back just a little bit. Is what I would have here is the magnitude of u, magnitude of v, cosine of the angle theta between them times vector v, all divided by magnitude v, magnitude v. All I did there was rearrange. So let's see, it's a little hard to see here. All I did there was rearrange. Okay, those terms. We okay with that? But what can I replace this expression up here with? That's what I've been building towards.
Dot product.
Dot product. So that would just be u dot v. That's a number, right? Oh, did we talk about this? We haven't yet. How can we save this? Let's do this. Divided by vector magnitude v, and then again I'm going to put the number 1 in there in a clever way. Okay? Times the cosine of 0. What's the cosine of 0, folks? 1. Right? Okay. Times vector v. So first of all, folks, I know that I'm getting a lot of nods. That's great, but I also know sometimes people miss things. Let's make sure we've got the right type of object here. What's the result of doing this dot product? A number. That's a magnitude, number. All we have here is a number times vector v. So this is just a scalar multiple times vector v. Everything's good. Okay? So at long last, what's this? Well, oops, folks, I wrote cosine of theta. I meant to write cosine of what?
0.
Cosine of 0, the number 0. Why did I pick 0? Because what's the angle between vector v and vector v?
0.
0. So that's the result of just doing v dot v, right?
What?
Let's ask that question. If I asked you to do v dot v, what's the definition of the cross product with geometry? It's the length of the first one times the length of the second one, right? Times the cosine of the angle theta between them. But what's the angle theta between these? 0. But what's the cosine of 0? So what I'm showing you here then is how we could take from here and get back to here. Okay. Again, I don't think that you should be saying, I see why you're doing this. All I'm asking you to say is I can follow the steps. Because the only reason why they do this is most people argue that this is a better formula than the one I gave you to begin with. I actually kind of disagree because this seems intuitive, it was easy to build, but this is set up to be in terms of our vector operations. So they're equivalent formulas, and so that what I'm saying is if you look up any book, what's the formula for computing the projection? That's what they give you, and I think it's lost as to where that formula came from. Okay? It came from this geometric picture right here of computing this length through trigonometry, and then saying it must be in the direction of this vector. And then it was just some clever rearranging. And I'll have to admit, folks, every semester I got to rethink, how do I rearrange this into this weird looking formula? Okay. How are we doing? Let's do some practice. Okay. So for this vector right here, and we'll come back and fill in some more notes. For this vector right here, we've got, here's vector u, here's vector v. First of all, we should all agree that this black vector right here is the projection, that black vector right here, that's the projection of vector u onto v. Does everyone see that? That's what we spent the first few minutes doing this kind of conceptual understanding. Okay? The problem is that we cannot easily figure out what this vector is the way we were able to do before because everything landed just so on our coordinate system. Okay? So our goal is to come up with that black vector right there. Folks, I'm sorry, I haven't gone through and erased it. The answer is right there. Pretend it's not. That's what we're trying to come up with. Okay? We're trying to come up with that. So how do we compute the projection of vector u onto vector v? We're going to use this nifty formula that says we're going to take u dot v divided by v dot v and scalar multiply it to our vector v. Where did that formula come from? It kind of doesn't matter. Right? Because we built the intuitive formula, which is worth knowing. Where did this intuitive formula come from? But then we did some tricky rearranging to come up with this other version of the formula. And that happens a few times in this class, where I say, you need to know this formula for an exam, but where this formula came from doesn't really matter. This is a cooked up way of giving you the formula, and it's a long ways away from the original intuition. Okay? So anyway, we got a formula. Folks, what did I say the easiest part of this class was?
Setting of
No, that's the part.
The setting of the first step's the hardest part. What did I say the easiest part of this class was? The computation, right? Now it's plug and chug. If I want to do u dot v, I'm going to do that multiplication up here. That would be 4 times 3, which is 12. 1 times 4, which is 4. Sum them together, and we get 16. In the denominator, I'm going to take v dot v. 3 times 3 is 9. 4 times 4 is 16. Their sum is 25. Okay. Times my vector v. If we were to go ahead and give this as perform the scalar multiplication, then we would end up with 48 25ths, comma, 64 25ths. What does that represent? This black vector right here. So again, I've kind of poked fun at the computation. You do have to be able to do it. You'll get plenty of practice with that. But conceptually, what did we just do? We just took this red vector right here, and we thought of collapsing it onto the blue vector, and we got a new vector, and that's what it is. How we doing, folks? The next part is to talk about just the length of the scalar projection. Okay? Well, we actually came up with the length very early on. How did we come up with the length of that scalar projection? It was just trigonometry. The length of the hypotenuse times the cosine of the angle between these vectors. Okay? So we're going to call that length the scalar projection. Okay? So it's a scalar whose length is however long that projection vector is. Okay? So in terms of formulas, do you see that the scalar projection would be sort of this answer right here? No, we'll just rebuild it. Okay? So we started off by saying, what was the scalar projection? It was just this. The length of vector u times the cosine of the angle between them. Okay? This, to me, is a very conceptual way of saying, how long is that blue line right there, right? Okay. The next thing is to just do some clever rearranging. Okay. And so whenever you see something like a cosine, you might be able to somehow replace that cosine of theta with a dot product. So what we'll do here is we'll take u cosine theta, and we'll multiply it. Careful, that's just regular multiplication here, folks. Okay. Just emphasizing that regular multiplication. We'll multiply that with the magnitude of vector v divided by the magnitude of vector v. Again, why? Because I wanted a magnitude of vector v in the numerator, so I gave myself one I wanted, and then I paid for it. Okay. Doing some rearranging, we're actually done. What's the numerator rearranged to be? The dot product, and then we have that in the denominator. So again, I don't think this is the most intuitive formula for how long was that vector we were just working with. Okay? This answer right here, if I said what's the magnitude of that vector, that's the scalar projection. Okay? Here is a very concise way of computing it. It's the minimum number of steps it would take to compute that length of that vector. But when you look at this, you're like, where did this formula come from? Okay? And we call that the scalar projection of vector u onto vector v. Okay? I don't see that all that often. This notation I see in all sorts of books. This notation I've seen in ours and just in a couple other places. We don't use this notation all that often. But all I'm saying is what was the length of that projection vector? And this is a formula that computes it very quickly for us. Okay? Again, I hate to say it, but I don't really care where this, like this formula is just a formula. You plug and chug. Conceptually, where do we start with? I think I lost an equal sign there. What happened? I don't know if I'm probably crazy. I feel like there's gremlins in this thing sometimes. I thought there was an equal. Was there an equal sign there at one point? I never put an equal sign there. Thank you. Thanks for keeping me honest. Okay, this was what we started with. This to me makes conceptual sense. And then all I'm doing is rearranging this into a more easily computable formula. Because it's actually quite a lot of work to find the angle between two vectors. So this is a more easily computable formula. Okay. So if we were to go ahead and use that formula and compute the scalar projection of vector u onto vector v, that's just going to be u dot v divided by the magnitude of v per this formula that we derived here. Okay. Again, all we're doing here, folks, even though I'm giving you this formula, is finding the length of this black vector here, which is what we just found right here, right? So you could also just take the magnitude of this, right? Square this component, sum them together, take the square root, you'll get the same answer that we're about to get here. This is what I mean by this is just a shorter way of doing these computations. Okay? So if we do u dot v, we just did that, I think it came out to be 16. The magnitude of vector v was 5, and there's our scalar projection, which is that. There it is. Okay. Folks, I'm not going to lie. These are kind of the grumpy days of teaching Calc 3. Like, I don't like this stuff. Not because it's not important, not because it's not interesting. I love this topic. But we've got, like, this topic is a huge can of worms, right? And we're trying to quickly get into calculus. If you haven't noticed, we haven't done any calculus yet, right? We've been doing some new math. We haven't done any calculus yet. So we're trying to get you exposed to vectors as quickly as possible so that we can start the calculus, which we're going to actually start. You're going to start in your pre-work tomorrow, right? We're going to start doing some calculus. But I'm having to rush through this, and I know that it feels like a rush. That's just kind of the nature of this course, okay? So there's a lot to learn in vectors. You learn more about them in other classes, and we will do some more work here when we come back from the break. But I know that right now it can be a little bit frustrating. Again, it's 3:42, so if we could start back up at 3:53, that would be great. If you didn't get your name, your note card at the beginning, come find me. Seth.
So I emailed
Blake,
you up
oh yes.
from last week.
Yes, Blake, welcome. Here's your name. If you just put your name on name, first last third name there, and then if you can get the other information that I pass along to other people to add to it.
Sounds good, thank you.
Christian, how we doing? Cordova. See you. Joseph.
Is it, oh, so
U.S.
it's
version of
charging?
the office. I agree.
It's pretty good.
Yeah.
Are you gonna go back or no?
Thinking
Okay,
about
I'll
it
see
the other
you
day.
later then. I'm in
Is
class.
Jonathan here? Hey, welcome.
Hey, I'll be back, I need to go to the bathroom. But I'll talk to you about that problem, cause
You still didn't?
I didn't get it, but it's me.
Okay, yeah, we can work through the whole thing. Yeah,
Alright.
once you see what
I'll do that.
Well, let's go ahead and resume. The next thing I want to look at is a couple of applications here for being able to do these projection vectors and then some just additional engineering applications. So the first thing is I'm not going to lie, this isn't, let's see, actually let's be careful here. For some two vectors, you express some parallel and orthogonal to be, yeah. This is something that you will do in a lot of physics classes. I don't do it all that much, but it's, again, this is the applications portion of the course. So I could give this vector u here. And let's just go ahead and give a quick sketch of vector u. Here's 4, here's 3, and here I've sketched, let's do it in blue here. There's vector u. And then I could sketch vector v. Vector v is the vector 1, 1. So that would be this vector right here. And we're asked to express vector u as the sum of two new vectors. Okay. We want to rewrite vector u. Let me go ahead and label these. This was my v here, and this is vector u here. And what I want to do is I want to write vector u in terms of its components that are well, not components as in these two orthogonal lines, but instead write vector u as the sum of two vectors, one which is parallel to vector v here, and one which is orthogonal to vector v. Okay? So one way to think about that is if I were to draw a brand new coordinate system, this axis that I just drew is what? What's that? Well, it's parallel to vector v, right? Okay. And then I could draw a new axis this way. And what did I just draw? Another axis that was perpendicular to vector v. Okay? So what I'd like to do is I'd like to be able to express vector u in terms of two component vectors. One which is, I'll put it here, one which is parallel, oh, it's a little too far. One which is parallel to vector v, and one which is orthogonal to vector v. So I want to give these two vectors that I could think of. So this would be my, see, do I call it just P and N? I call it P and N there, folks. Yes, P. P for parallel, and N for orthogonal. Okay. So I want to be able to write vector u not in terms of I hat and j hat components, but in terms of a component that's parallel to vector v and a component that's orthogonal to vector v. Okay. Which of these seems to fit with something we've just been talking about? Which one?
P.
I think the P, the parallel one, is really, P you could think of as for parallel, but it's also just the projection of vector u onto vector v. So we notice here that P is equal to the projection of vector u onto, vector u onto vector v. Okay. Does everyone understand that? Would you like me to kind of re-explain this image, what we just did here? We okay with that? Do you want another explanation? Yeah, let's talk through it, folks. So I put vector v on here, and what I'm doing is I'm creating a new coordinate system based on this black vector v here. Okay. One of my axes will be parallel to vector v, and one of my axes will be perpendicular to vector v. Is everyone okay with that? So then what I'd like to do is I'd like to refer to vector u not in terms of, say, 4i plus 3j. That would be in terms of x and y components. I want to refer to it in terms of these new coordinates, which we could call the parallel and normal axes. So it's like we've created this new axis, and I want to refer to vector u. It is true that vector u is the vector, 4, 3. So that's the same thing as saying that it's 4i hat plus 3j hat in terms of those components. But I want to write it in terms of its parallel component and its normal component. Okay? It's kind of like giving a new coordinate system for this. Folks, I actually think this is a very complicated idea, and it takes a while to get used to it. And I'm sorry we're going to get one kind of pass at this, one example of this. So we'll give it our best shot. There is a detailed solution that you can take, and I'd be happy to answer questions outside of class on it as we're working through this. Yes?
Something like this be on an exam.
I need to be a little bit careful with this because we build some other things, like we're going to have tangential components of acceleration and normal components of acceleration. So I need to be a little bit careful with this. I won't say that, I'm not going to explicitly ask you to break things up into parallel and normal on this first exam, but I'm not saying that this is, yeah, you can be a little careful saying, I wish I could say blanket statements in math, but it's kind of hard to do sometimes. Yeah, so let's go ahead and find this projection. So folks, we developed this formula, okay? I'm not going to lie, I don't have this formula memorized. Oh, well, it's obvious there. There. U, and then v dot v, and then vector v. Right? That's the projection vector formula. I don't have that one memorized, I'm not going to lie. I build it each time I need it. Okay? All right. So if I do u dot v, that would be 7. And if I do v dot v, that would be 2. And then we multiply that to vector v. Folks, I'm sorry to spend so much time standing in front of the board. It just works. I find that writing on the side is what gives me the problem. So with this new board. So this is the vector 7/2, comma 7/2. What did we just find here, folks? What did we just compute? This vector p right here. Does everyone see that? Okay. And then let's go ahead and find our normal vector n. Now, what you could do, when I was trying to remember how to do this last week, what you could do is you could come up with this line right here, right? You could find the equation of this line, right? This has a slope of 1, this is the line 1, 1, right? And so this would be a line with a slope of -1 in this case, and then you could project vector u onto this. You could start all over, right? You could start all over to build it, but you don't have to. Okay? You could also argue that this constructed a right triangle and use your Pythagorean theorem on it. Another way you could do it. But even easier, what do we say we're expressing vector u as? The sum of these two vectors. Do we know what u is?
Yeah.
Yeah. Do we know what p is?
Yeah.
So let's just solve the simplest vector equation to find out what n is. Okay. So to find n, we're going to use the fact that u is equal to p plus n. U was the vector for 3. P was the vector 7/2, 7/2. And then we're going to add to that this vector, which has two components, n1 and n2, and we can solve for those two components. Okay with that? Yeah, Christian.
Wait, could you actually go back to my n vector equals p plus n?
So what we're trying to do is we're trying to write vector u in terms of the sum of these two vectors, right? So what I did, if you were to line up vector p, and then put vector p there, and then put the tail of vector n at the tip of vector p, like I've drawn there, then their result needs to be vector u. So that's all I'm saying is that when I add these two vectors together, I need to get to vector u.
Okay.
Yeah, great question. My plant in the audience, I appreciate it. Okay, other questions? Christian says you're going too fast. Yes, Isabel.
You'd subtract, P from.
Oh, of course, yeah, there's lots of ways you could have write that. So what you could have written here is you could have said, then n is equal to vector u minus vector p. Yes,
And that would give you vector.
that's going to give me exactly what I'm about to do right here. Yeah, exactly. Because when are vectors equal? When they have like components. So we're just going to be combining components. So we've got 4 minus 7/2. Okay. Help me out here, folks. 4 minus 7/2 is equal to 1/2. And then we would have 3 minus 7/2, which is -1/2. And that's our vector n here. And that should fit with our little image that we drew. You notice that? That seems to be a vector pointing in that correct direction? All right. Folks, I've not had to deal with this much in my life, but in the engineering and physics world, your life is greatly simplified by picking the correct coordinate system, right? By referring to the origin in the right way. And this gives you a way of kind of creating your own new coordinate system in terms of a vector that's parallel to this vector v and normal to this vector v. We'll look at an example. Of how we use that in a moment. Okay. We talked a little bit. I think we talked about work in our pre-work, right? I gave you the definition of work in our pre-work for this. The shorthand is if I know a force vector and I've got a displacement vector, then the work done is just their dot product. In earlier physics classes, you might have said that work is force times distance, but you got to be careful because it's only the amount of force that's in the direction of motion, in the direction of the displacement, and so that dot product does exactly that. Okay, so here, this is actually, I don't think we had this example, but did we have this example? No, it was different in your pre-work. So here we've got a suitcase is pulled along 50 feet along a horizontal, so here's our horizontal sidewalk. Here's our suitcase. And it's going to have a displacement at 50 feet. So we're gonna have a displacement vector like this. What's that vector right there? That would be the vector 50 comma 0. That's the displacement of this suitcase. Then we're going to apply a force to this suitcase, and our force is a force of 30 newtons, or excuse me, 30 pounds, at a direction of, or at an angle of 30 degrees above the horizontal. All right. Now here's the thing to remind you of, because I just drew this kind of how I imagine as I'm reading this physical situation here. I've got my displacement vector, and there I can think about this force vector that it's like I'm tugging on this suitcase. But when we go to set up this problem in a physics class, what we do is we set up our vectors right here. Oops, not that steep. We set up our vectors like this. That's the picture that goes with this problem. Of course that works because why? Vectors don't actually have location in the plane, right? A vector just has a magnitude, a length, and a direction. So I can align these vectors however I want, and now we can just think about taking the dot product of these two component vectors. Or excuse me, these two, I said component, I meant to say position vectors. Of these two position vectors. So this is the position vector, we already knew this to be the position vector 50, 0. But what do I need to do now? Well, I guess I have a couple of options here. One is I could actually break this up into its two components. I could call it the force in the x component of the force and the y component of the force. And that's similar to that brute force method that you did in your pre-work when you were doing the tension in the cable, right? Does everyone see how I could find f sub x and f sub y? Because we're not going to solve it that way, but does everyone see how you could do it this way? What do I mean by that? I mean that f sub x would be equal to 50 cosine 30 degrees, and f sub y would be equal to 50 sine of 30 degrees, and I could find those two components, right? Then I would have a component vector, and now I can multiply these two component-wise, right? The other way we could do this is how, and this is how I'm going to do it. It's just based on the information we were given.
Project F onto D.
We could do that. Let's just use our geometric definition of the dot product, right? Because we're trying to compute work here. We're trying to compute work, which is equal to force dotted with displacement. And how do we take the dot product geometrically? We take the magnitude of the first vector, that's its length. Do we know what the length of our force vector is? What's the length of our force vector, folks? 50. Times the length of our force vector is what? Not 50, but 30. Okay. What's the magnitude of our displacement vector? 50. Times the cosine of the angle between them. Right? That's just the geometric definition. So here we go, we would have 30 times 50 times the cosine of 30 degrees, which is equal to 150 times the square root of 3 over 2, or 75 square root of 3, and our units on work. Oh boy, it's digging deep. Work's Newton meters, right? Oh, foot pounds in this case. Thank you. Foot pounds in this case. We're feet and pounds. Thank you. Yes.
It'd be 30 times 50 would be 1,500, not 150. Right?
Oh, did I make that same mistake again? This is not my first time making that mistake. What's 30 times 50, folks? Help me out.
1,500.
1,500. So 750 square roots of 3. Thank you. Yeah, appreciate that. How we doing, folks? So do you see, there's lots of ways to, I need a better phrase than that. I don't say skin anything. There's lots of ways to make the vectors align, okay? Lots of ways to make these vectors align. You could have broken it up into components, and then you could have done the dot product by just taking the x component times 50 times the y component times 0. Notice because the y component would be times 0, that would be the same thing as just projecting the force component down into the onto the x-axis, and then giving that projection vector. and then finding its magnitude. How we doing, folks? Okay. So let's get an application for these parallel and normal forces. Suppose an object lies on an inclined plane, then the force due to gravity points which way?
Down.
Downwards, as it always does. Okay. If we project the, let's see here. Well, let's see. We want to project the force due to gravity onto a vector that is in the same direction of the plane. We get the force parallel to the plane, and the force perpendicular to this is called the force normal. So let's go ahead and compute both of those. So the picture that goes with this, folks, is we've got this regular coordinate system, but then we've got an inclined plane. And I think we're supposed to do this all in terms of, I want to put theta in here. Yeah. So here we've got an inclined plane with some angle theta. So although this isn't a vector, we could give a vector that's pointing in the same direction of this inclined plane, and that fits with our idea that we introduced before. So if we had this, let's say we had this box sitting on the inclined plane. Okay. The force due to gravity points which way?
Down.
There's our force due to gravity. Okay. It's a vector whose x component is what?
0.
0, because it only has horizontal component to it. Okay. What we'd like to do is we'd like to, instead of referring to things in terms of the x and y coordinate system, we'd like to build a new coordinate system on our inclined plane. And that's the benefit of doing these projection parallel and normal vectors that we looked at in the previous example. Is this coordinate system works great if objects are moving, just on the ground or moving up. But here we can insert this inclined plane, and so we want to refer to coordinates along this plane. Is kind of a more natural way to do it. And so what we're going to do is we're going to build a new coordinate system that looks like this. Okay. That's going to be our new coordinate system that's aligned with the plane instead of the original x and y coordinates. Okay. And to be honest, folks, I'm not going to lie. I don't do this. Okay. You do this in physics. You do this in engineering. You do this all the time in those. But I don't do this much. Okay. But you could imagine why you would want to give coordinates on this axis rather than this axis. Okay. So what we'd like to do is we'd like to refer to the force due to gravity in terms of having a force component parallel to this inclined plane and normal to this inclined plane. So the force parallel to the inclined plane would be this force right here. That's our force parallel to the inclined plane. And then we want a force perpendicular to it. Well, we've already used P for parallel, so we'll use N for normal, which means the same thing as orthogonal or perpendicular in this case. Okay. So all we want to do is come up with these component forces. Okay. And what could we do here? Let's see, what did they do? Yeah, okay. So if we want to come up with the force parallel first, let's do that. The force parallel is just going to be the projection of our force due to gravity vector onto V, where what's V going to be? V is just going to be some vector. V is just going to be some vector pointing in the same direction as this plane. So for example, if I knew the slope of this plane, maybe I could use the vector, if the slope of this plane was m, I could use the vector 1, m, and that would be that vector. If I knew the slope of the plane, the slope of this line was 3, then I would have the vector 1, 3. Okay. So this would be the vector v that we use, and that gives us the force parallel. How are we doing, folks? Now, again, when I was trying to remember how to talk about this, I was thinking, oh, I'll come up with the equation of this line right here, and then I'll project the force due to gravity onto that line right there. Would that work to find this force normal? Yes, but it's working harder than we have to. How come? Because under this new coordinate system, we have that the force due to gravity has to be equal to our force parallel plus our force normal. So all we have, what we have is we already have. What we already have is two of the three vectors that we want, and we just solve for the other one with vector subtraction. Yes?
Why is f of g equal to the parallel and normal force?
Well, so there's lots of ways to look at it. One is by our parallelogram rule. For the picture we just set up here, the parallelogram rule for vector addition says that if I want to add two vectors together, I could sketch, I'm going to run out, I'll put it on and then take it right off. I could come up with the parallelogram spanned by those two vectors, and the sum is the result. Well, because the result, or because that meets, the force due to gravity meets in the same place there, it must be equal to the sum of those two vectors. The other way you could do it is if you wanted to, you could set it up tip to tail. If I took force normal and set it up tip to tail on force parallel, I'd get to force gravity. Yeah. So and that's basically, it's the same way as like, if I just had this vector right here, maybe this is the vector whose tip is at a comma b, we would say that our vector could be thought of as a scalar multiplied to I hat plus b scalar multiplied to j hat, because what we're doing here is we're going to take I hat and then scale it out, and then we'll take j hat and then scale it out. And so just like we always represent when we're in the xy coordinate system, we can always break any vector down into its x and y components. For any pair of vectors, we can break a third vector down into its components for those other two vectors. But it's convenient that we specifically took vectors that were perpendicular to each other. We like our coordinate systems to be perpendicular to one another. Great question. Oh boy. All right, let's keep going. So there's an old rule that I'm supposed to know, righty-tighty, lefty-loosey, that has to do with like when you're tightening a bolt or you're trying to loosen a bolt, right? If the bolt's stuck, you got to know which way to twist it. Okay? This is the same idea. We're going to look at torque here, and we're going to think about applying a force to a lever arm, and that's going to generate something called a torque. Okay? So if you want to think about it, if you take a screw with a screwdriver, and I know some of you already know this. If you just hold up, because some of you haven't thought about it before or seen it before or had a physics class on it before. If you take a screwdriver and you twist a screw, what does the screw do? Well, if you twist the right direction, the screw gets driven into the wood, right? You're creating a. No, that's not quite what I was saying. Let's just work with this picture here. So if I go ahead and think about there being like a hex head bolt. That's not a hex head. If I think about there being a hex head bolt on the origin, like so, okay, and if I take a wrench to that bolt, okay, if I exert a force on this wrench, so let's exert some sort of force on this wrench, okay, that's going to generate a torque on that bolt, which will either drive the bolt into the wood or twist the bolt out of the wood, right? Maybe you've tried that before. Does everyone kind of have a real world sense of what I'm talking about? I don't know. Okay, great. So we could think of this, we could create a vector right here that we'll call R. This vector right here we'll call R for the what? The radius of that wrench. Okay, we're twisting about this, but we think of that as the radius of that wrench. Okay, and then we're going to go ahead and apply a force of F on that wrench. Okay, that force just has a magnitude and a direction. Okay, By the way, this would not be the ideal force to apply to this wrench to generate the most torque. Right? What should be the direction for this force to generate the most torque? It should be perpendicular to it, straight down. That'll generate the most torque. Okay? That has to do with the cross product. Okay? So the torque, and in fact, let's see here. Let's go ahead and strip the picture away. So there's our radius, and there's our force. So R and F. Okay. So the torque is going to obey the direction of the torque will obey the right-hand rule. Okay. So let me just give you the let's see here. That is torque. Let's see here. I want to do torque in red. Torque is equal to the magnitude of our R cross F. I should have done the F in a different color, but I didn't. Let me just double check that. Yeah. Oops. I apologize, folks. Folks, I apologize. It's not the magnitude. It's just the vector itself. It's just the cross product of those. Sorry about that. Okay. So, folks, the torque that's going to be exerted, which is like the driving force that you're putting onto this bolt, is equal to the cross product of these two vectors. Okay, your radius vector and your force vector. Okay. So let's just ask the question, based on the picture that I drew, which way is this bolt going to go? So here I've got maybe you can think of this as your x-axis and your y-axis. My z-axis is coming out. Let's make sure we're oriented correctly with the, my z-axis will be coming out this way. Okay. So which way is this bolt going to go?
Clockwise.
So the problem is inside this plane here, right? We're in the xy plane here, and we want to compute R cross F. So with our index finger, we point in the direction of the radius. With our middle finger, we point in the direction of the force. And so our thumb is going to point in the direction in which we exert the torque on this bolt. And so this bolt is going to be driven which way? Out of the screen or into the screen?
Into the screen.
It's going to be driven into the screen. Okay? So that's the explanation of that righty-tighty, lefty-loosey rule, which I never quite understood. Yeah?
I'm confused by that. Let's say it's not a screw and it's a tire. We can still apply torque, but it's not gonna move orthogonally, like towards us or away from us, right? Isn't that due to the physical nature of the, spiral structure on the screw, not the fact that we're applying torque to it specifically?
So,
Let's say I apply torque to a wheel. The wheel is going to spin, but it's not gonna.
so careful. So what do you mean when you say apply torque to a wheel?
So I could take a giant wrench like that and turn it. That's torque, correct?
Yeah. So I'm gonna go ahead. I'm gonna have to back off a little bit because I don't know torque, right? I know this definition. If somebody else want to take a shot at it, because I folks, the last time I had a physics class was 21 years ago. Okay. So I'm not sure of the physical definition of torque. All I can tell you is this vector definition of torque. And so when we start talking about the direction in which the torque is applied, right, the direction of the torque vector, the direction obeys that right-hand rule. My explanation about the bolt being twisted in or twisting out, that may not be a correct explanation. There may still be some sort of you're talking about the way the braid was put onto the screw. I'm not sure about that explanation. So as far as the torque vector though, the torque vector is going to point either out of the plane or into the plane. And in this case, the torque vector would be pointing into the plane because of the direction of our force. I don't have a better explanation than that. I can work on it if you'd like. Somebody have something to add to that?
Just
to be helpful?
like, think of torque as like a angular component of force. So it's like
An opposite, but we chose that, so it's sort of just like a human convention, I
So,
guess.
yeah, so I guess I could ask, like, I think that we set up the threads so that a positive torque results in it being driven inward. But I'm asking you, where is this, like, but we could have set up the thread so that a positive torque would twist it outwards. But the question is where is the positive torque? And in this case, positive torque is pointing into the page.
I have thoroughly confused myself.
That's okay. I'd like to move on.
Look on my phone.
Yeah, please do as you wish. I'd like to go ahead and just move on, folks. I do not know torque as a physical construct. I only know it as a vector that we get through this cross product. So I apologize for that. That's luckily why you have physics classes and not just the math classes to go with them. All right. I have a couple more things I want to add here real quick. Just like a rectangle, the area of a parallelogram is its base times its height. For two vectors in R3 then, the magnitude of their cross product, this is what we were looking at a little bit ago, is the area of the parallelogram formed by these two vectors. Okay. Folks, I just said that really fast. That's back to this demonstration that we were looking at before. Okay. So the magnitude of the cross product is just the area. So I'm talking about the length of this cross product vector here. It's just the area of this parallelogram. So we could ask this question, and we're not gonna all go all the way through it. The answer to this question would just be to compute U cross V, and then take its magnitude. Take U cross V, compute its magnitude. That would be the area of the parallelogram spanned by those two, because that's how we define the cross product. Okay. So here we have a way of computing, if we know the angle between two vectors, we've got a way of computing the area of that parallelogram. Okay, just by using standard trigonometry. Would we just say the area of the parallelogram is what? Base times height. Its base would be the length of this vector B here. Its height would be the magnitude of A times the sine of the angle between them. Okay? So here we're ready to kind of finish out that definition of the cross product. The cross product of two non-zero vectors in three space is a vector orthogonal to both, constructed so that the magnitude is equal to the area of the parallelogram, formed by the two vectors, and the direction prescribed by the right-hand rule. Okay. So here is a handy formula that we sometimes use based on everything we just said. This is the magnitude of the cross product, but we just said that the magnitude of the cross product is the area of the parallelogram, and we would compute the area of the parallelogram this way. Okay. So here you can see a kind of a geometric argument. If the angle between two vectors is either 0 or 180 degrees, what's their cross product? 0, because the sine of 0 degrees, sine of the sine of 0 radians, sine of pi radians is 0, and so there is no cross product. And that's exactly what we were seeing in this demonstration when I brought these to be pi radians apart or pointing in the exact same direction. The cross product was 0 because its magnitude was, let me say it like this, the cross product was the 0 vector because its magnitude was 0. All right. Folks, here's a we're going to move on. There's a video solution to me working this. This is one of your MyLab math questions. And the last thing I want to say is, one thing I think you should be a little bit skeptical about is what relates our component definition of the dot product to the geometric definition. That's the last thing that I haven't explained, and we're out of time, so we're not going to. Okay? But I've got a worked out solution where I show you, basically we developed this from the law of cosines, and I'll show you what relates the component definition to the geometric definition. That is, when I say u is equal to the vector u1, u2, and v is the vector v1, v2, we have two ways of computing the dot product, right? They are u dot v is equal to the magnitude of u, magnitude of v, times the cosine of the angle between them. That's what I'm calling the geometric. And then we have that this answer would be u1 v1 plus u2 v2, which is what I'm calling the component / analytic. Oop. How are we doing, folks? Okay. So you should have that question, like, wait a minute, how come I can compute this two different ways? What relates them together? And the law of cosines is your starting point for showing that these two compute the same thing, that this expression here and this expression here compute the same thing. Okay. How are we doing? All right, it's time to move on. I'm going to hold off giving you one. Great. Michelle, give you one then.
Yeah.
What's that?
Samsung SC.
So what? Oh, I don't think we skipped. Yeah, we skipped over a little bit. This has a video solution, and this has a built-in solution at the bottom that you can click. So the two things I skipped both have solutions. Oh, thanks. What's that?
This last page.
Question 40 and beyond.
Oh, yeah. Those are for you to try. Yeah. If we had more time, I would give us some time to work some new groups. They could be part of that? Did everyone get a copy? Did anyone not get a copy of this? All right. Folks, I had some people ask about this last page here, or these, maybe it's 2 pages, 7 and 8. Please give them a shot. See what you can do. We've covered everything in here. Give them a shot. Come by and see me with questions on it. Okay. All right. They're just kind of more examples of those. Okay. So we looked at our pre-work last night, and we had 2 topics. One was lines and planes, and the other was our quadric surfaces. So let's go ahead and remind ourselves, what was the vector equation for a line? How are we going to give a vector equation for a line? So the picture that we started off with was we could think of a line as a collection of tips of vectors, right? Eventually, we got down to this vector equation for a line where we said r is going to be a vector that's on our line, or it's equal to r naught plus some direction vector times some scalar multiple t. Okay? So notice that this gives us r naught plus some direction vector times t, and sometimes I'll interchange those orders, folks, just kind of as needed. I think I probably wrote it the other way earlier. Okay? We'll interchange that scalar multiple. But this gives me a new vector, right? Which is r. And r has a point to it, a tip. And that collection of all those tips, all the vectors that satisfy this equation here for all values of t is our line. Okay? The way we think about this is we've got this, this would be our r here, and we can think about taking some initial r naught and adding to it some direction vector. Okay? So folks, that's a real quick explanation. If you want a more thorough one, I recommend going back through that pre-work. But the way I want to talk about this is I'm going to take this direction vector and I'm going to scalar multiply it by some number called t, add it to this r naught, and it's going to give me this new vector, which I correspond with a point on my line. Okay? It is a new way of thinking about lines. It's the best way to think about lines because it extends quickly to higher dimensions. Okay? So yeah, the way you learn lines in algebra when you were doing it on the xy plane, perfectly good. But we're not in that space. We're going to be in 3 space and higher, so we need this other way of working with lines. Okay? So let's go ahead and find the equation of a line passing through these 2 points, and let's represent this line several different ways. Okay? So the key here is, what do we need if we're going to give the equation of the vector equation of a line? There are 2 things.
Magnitude, direction.
Careful, because it's not just a vector, right? It's a collection of vectors. So we need a initial point that we pass through. Okay. So that what we need, and I think I summarized this. I'll summarize it down here. But what we need is an initial point that we pass through. Do we have a point that we pass through?
Yeah.
In fact, what? I've given you. So folks, I'm pointing this out because these equation of line problems are all the same in that you build the equation of a line because you find a point that you pass through and you find a direction vector. But sometimes we insert extra hurdles in that process. Always you're looking for a point that you pass through. In this case, I gave you one. Okay? We also need a direction vector. Do we have a direction vector? Not yet, but what? We can go find it. So we also need a direction vector. So let's pick one of these points that we pass through. How about the point P? Okay. So let's use, for this we'll use P. And we need a direction vector. Well, the direction vector is this vector along here that points along the direction of our line. So notice that the direction vector does what? It passes through 2 points on our line. Okay? So for the direction vector, let's go ahead and use the vector, say, PQ. Okay? What if you use QP? Are you still going to get the right answer? Yes, you'll just be using a scalar multiple of the direction vector that somebody else picked. That's fine. Okay? So what's our vector PQ here? Let's build that first. What would be the vector PQ? So it would be the vector, I forgot about that. It would be the vector 4, 3, 2, right? And the point that we pass through, we're using P, and we can construct a vector for point P. Let me use, that's fine, let's change that to R naught. R naught. And that would just be the initial point that we pass through, and we pick 1, 2, 3. So let's give the vector equation of this line. It's just a collection of all vectors R that can be written in the form 1, 2, 3 plus T times 4, 3, 2. So what I want you to see is that, look at, this would be some initial position vector, like this R naught right here. Does everyone see that? Okay. And then here we've got a direction vector, like this black vector that I've drawn right here. Okay. When I add together the green and the black vector, I get a new vector whose point is, whose tip corresponds to a point on the line, right? But that would just be one of them. If I were to scalar multiply, if I were to elongate this black vector, as I'm adding it to this green vector, I'm getting all of the other points on this line. Okay? And so that t allows me to run through all of the other points on this line. So for this parameterization, this would be from minus infinity less than t less than infinity, and that's a way of describing this line here. Okay. Could I get